This video lecture is talking about sigma and pi bonds. We've been discussing hybridization earlier and thinking about how the different molecules and the geometries relate to this. So today we're going to talk about some of the specific types of bonds that we'll find in those. And again, this is talking about hybridization. Just a quick review of that. If you are thinking about hybridization, and we think about our carbon, and we'll start with, say, carbon with a double bond to oxygen and single bonds to hydrogen, and then we've got unshared pairs on the O. This is formaldehyde that they talk about in the textbook. If you notice around the carbon, there are 3 bonding sites. So we would expect that hybridization to be sp2. And then there would be an extra 2p orbital that is not being bonded with. So this sp2 orbital has three electrons in it. 1, 2, 3. And then there's 1 electron there on the outside. Let me clean this up a little bit. So there's our carbon double bond, and then here's our 3 sites. So our central carbon atom, since it has 3 bonding sites, is sp2. So that's a total of 3 hybridized orbitals. Remember, there's still a 2p orbital that's sitting out that's not hybridized. So there's our 4 different types of bonds that carbon makes, and there's 4 bonds on that structure. So that sp2 hybridization allows it to account for that geometry and how those mix together. So how does this exactly go together? And how does this work with oxygen? Well, some of these bonds are going to overlap parallel to each other, and some are going to be almost perpendicular on the electron clouds. And that's what sigma and pi bonds really talk about. So we'll come back to this hybridization idea here in a second, how this looks in the geometry. First type of bond is called a sigma bond. This is a single bond. This is where that sp hybridization overlaps and is cylindrical, is how it's described. Parallel, straight across. All sigma bonds are always single. You've got a nice picture of that here on the left side of the screen. The other type of bond that you'll see is called a pi bond. Pi bonds are perpendicular to the axis of the nucleus. There's side-to-side overlap, and there's electron density above and below the axis. Sigma bonds are always single. Pi bonds have to be present if it's a multiple bond. This diagram in your text talks about where you find sigmas and pi's. Single bonds are always sigmas because sigma overlap is greater. So you have more overlap whenever you have a sigma bond. And it's always stronger. So notice here in our hydrogen, we got a single bond, sigma, where they're overlapped together, and it's parallel across the side. In a multiple bond, there has to be 1 parallel overlap, or sigma overlap, and the rest has to be pi bonds. Talk about here in the middle picture that this has 1 sigma bond and 2 pi bonds that are above and below the axis. The triple bond of nitrogen has to have 1 sigma bond and 2 pi bonds to account for all of it. This picture that we just talked about with CH2O, or formaldehyde, shows that carbon is sp2 hybridized. And notice in the middle that one of those orbitals, one of those hybridized orbitals, is going to overlap with the oxygen orbital because it has 3 bonding sites on it. You've got carbon-hydrogen single bonds, which makes them sigma bonds. And then there's a carbon and oxygen bond that becomes a pi bond. It's not going to be once, as soon as you overlap once parallel, the other overlap is going to end up being a pi bond. Now, how in the world does that look with our hybridization example? So let's go back to thinking about how this looks hybridization. Oxygen, it has 3 different bonding sites around it. So we would assume that it would also undergo sp2. So as it begins to overlap, it's got some 2p hybridization as well. One of these is going to go overlap together to make that single bond. Envision it kind of being that bond right there. Now, with the electron pairs of oxygen, it has unshared pairs on the outside. These two bonds here go with the hydrogen single bonds to the top. Because they're single bonds, they're going to combine with hydrogen's electron clouds. These are going to end up here with the unshared pairs of oxygen. What we end up with is we get this unhybridized p orbital that's going to make the double bond with it. So you have an orbital they're going to overlap, but it's not going to overlap side to side. It's going to be pi cloud. So notice we get a carbon-oxygen sigma bond here in the middle, and then we also get a carbon-oxygen pi bond from that orbital. Again, the unhybridized p orbital overlaps in that pi fashion. This is a triple bond. You have an sp orbital in the middle, because you only have two bonding sites. This structure here is C2H2. The Lewis structure looks like this. Carbon triple bonded and single bonded hydrogens. So to explain how this overlap works, there's a sigma overlap between the carbons, and then we have these p clouds, or the pi clouds over the top. We've got pi bonds above and below that are perpendicular to the surface. So this has one sigma and it has two pi bonds. So we get hybridization above and below the axes. So how does this work whenever we're trying to figure out the hybridization of different structures? If you're given a structure like this, and you do the Lewis diagram, and you want to think about the hybridization around a particular atom, and let's isolate this bond right here. This has a triple bond. So this has to have the overlap of one sigma bond because it's at least single, and it's got to have two pi bonds that go with it. That would be the hybridization. Those are the types of overlaps you would have. If you look at carbon, carbon has to be an sp hybridization because it has two bonding sites around it. So that means you have two p orbitals that are left over that aren't doing anything. Those become the two pi bonds because only one of those p orbitals is being used in the overlap. The other two p orbitals become pi bonds. If you had carbon dioxide, it only has sp hybridization because it has two bonding sites. So there are two p orbitals left that aren't hybridized for carbon. So when you think about how that looks, those p orbitals become these two double bonds. These single bonds, those are sigmas. Those are the overlaps between those clouds, that sp overlap on both sides. Those are singles. But the two leftover unhybridized p orbitals become the double bonds. If you get a structure like carbon monoxide, you would have one sigma overlap and you'd have two pi overlaps. Because again, you're dealing with two bonding sites for the carbon, for the electrons, sp, and then you have to have two pi's that are left over. So how does this all tie together? If you take something like CH4 and you do the Lewis diagram for it, and we want to talk about the geometry of this, there are 4 electron pairs. There are 4 that are bonding. This would have to be sp3 hybridized. If it's sp3 hybridized, there is no possibility of a pi bond. You have to have unhybridized p orbitals to make that happen. This would be all sigmas, and this would be tetrahedral in arrangement. Now change that and go to C2H4. that Lewis structure has a double bond, and you have 2 hydrogens that come off of it. 3 bonding sites around this carbon. So that would be sp2 for the hybridization. This is trigonal planar around this because it makes the flat triangle for 360. So we have 1 p orbital not hybridized. That p orbital becomes the above overlap for the pi bond. So this helps explain the Lewis structures. This helps explain the geometries, and it helps explain the orientation about each of the atoms by learning the sigma and pi bonds. Try not to make it too complicated. If you analyze it, that every structure has a sigma bond that's covalently bonded, and if it's double bonded, it has 1 sigma, 1 pi. Triple bond has 1 sigma and 2 pi's, because there are p orbitals not being used in the hybridization. That helps explain a lot of the structures and a lot of the geometry. We'll talk more about delocalized electrons in class tomorrow. Good luck.